All right, so this lecture is going to be based on state space models, and we're going to go over like how they work, along with a visual example, and we're going to talk about like how they've evolved over time. So the main motivation for these models was to basically address like long continuous time series problems. So things like ECGs, speech, and energy forecasting are basically the main like types of problems that you might want to like solve here, especially speech, considering it's like recorded at about like 16,000 hertz a second. Like this leads to pretty long like this leads to pretty long continuous time series, and at the time models couldn't really generalize it. So like when the first state space model was like produced, it was like fairly influential. So some paradigms that were currently being used at the time for long time series were like continuous time models and recurrent neural nets and convolutional neural nets. So like obviously each of these have their own like pros and cons, right? Continuous time models are basically just like uh ODEs that do stuff. They have like a good amount of continuous data and they can sample irregularly, but the thing is, they're quite complex and they're pretty inefficient. And just like RNNs, they also suffer from like vanishing and exploding gradients. RNNs are great in the sense that they have an unbounded context, meaning you can kind of like continue like going forward, like just using the hidden state from your previous time step. But they also have inefficient training in the sense that like uh, you can't really parallelize like back propagation through time, for example. And it's also sort of difficult to parallelize RNNs in general. And then for convolutional neural nets, if you remember the CNN lecture from way back last semester, you might realize that the main motivation for RNNs was that CNNs had to basically restructure and increase and retrain if you wanted to get a CN, if you wanted to train for like a size of like the number of model parameters plus one, you basically had to make a new CNN. So even though it's like really parallelizable, it has a bounded context basically. And all three of these at the time struggled with long range dependencies. Obviously now with like, you know, like GPT-4o and stuff, they won't really struggle as much. Um, but when this paper was released, at least, uh, these were like some of the big problems. So a brief recap on attention here, before we get into state space models. So like this is your classic like attention operator here. It's just like your input u multiplied by the query key and value weight matrices, and you're dividing this by the dimensionality of your query and key like query and key matrices, and you softmax that whole thing. So the important thing we want here is the dimensions of each of these matrices. So the query and key matrices have dimensions of L times D, where L is like the length of your sequence and D is like the dimensionality of these matrices. And same goes with value, the value matrix. So matrix multiplications are very parallelizable on like RNNs. But instead, when you do these like matrix multiplications, attention, this equation that does attention is essentially O of n squared, assuming you have a fixed like dimensionality. If your dimensionality is not fixed, then it's more than O of n squared. It's going to be O of L squared D. So if your sequence is pretty long, training and inference can actually be pretty expensive. So the core promise of state space models is to combine the parallelizability of a transformer along with the memory efficiency of an RNN. So this is a state space model, essentially. It has three representations, and it can switch back and forth between these representations, like sort of like whenever it wants. Usually, what people do is like they train it in the convolutional view, and then they inference on it through the recurrent view. And I'll get into how that works later. But like that's the interesting part of this is that it can like kind of switch modes and take advantages from each piece. So this is essentially the main equation of the state space model. And this, the image below is essentially like the continuous time model. So first, the first equation, it describes taking your input UT and expanding to a latent state. And it does this through a simple linear ODE. So like, just one note, like I'm gonna have an example after this, like a very visual example that shows like all of these matrices and stuff like that. So like, because the math is gonna get pretty complicated pretty fast. So like, the visual example should help. Now going back to this, like the first formula xt, it like takes your input, which is ut, and like takes your current state xt, and then tries to predict and gives you the next state, which is x prime t. So it's basically moving from one state to the next state using input and current state. Your output yt is generated from your current state and your d, which is like D is essentially a matrix that takes your input and then maps it directly straight to your output. You can think of D like a skip connection. But the thing is, you won't really see D being used too much in state space models, depending on what you're doing. Like, for example, if your goal is like language generation, a lot of people tend to just initialize D to 0 and just completely ignore it. They don't even bother training it. For other things, D can be pretty useful because it just gives you like an innate skip connection right there. So after this slide comes the visual example. So like if you like, I'm gonna like skim through the math a little bit here. But essentially you have like your two equations, and you first start by taking this continuous time model and you discretize it by like a step size delta. And the technique you use is called bilinear discretization, but like you don't really have to worry about that. Like it kind of does that. And then you get your discretized form. And this like equation is kind of what you're going to be using a good chunk of the time. You're most likely not going to be, you're almost never going to be using the continuous time form, because the discrete time form is kind of what you're going to be using when you start like training and inferencing. So here is the visual example. So assume like, oh, this is getting in the way. Okay, maybe that's better. I wish there was a way to hide this thing.
Yeah, hide floating.
Where? Oh, I see. Wait, yeah, okay. All right. So basically, let's assume that you were like essentially trying to model like a vehicle, right? So your A matrix describes like the state of the vehicle and how it like this change of the state of the vehicle over time. So like day t to day t plus one, like the A matrix would essentially like describe like the gas getting like a tiny bit lower, assuming you do nothing, by the way. This is not dependent on input, which is like maintenance in this case. But the A matrix would like describe like if you did absolutely nothing on day t, your A matrix would change like the values in your state, like maybe make the gas like a tiny bit lower, maybe make the oil a tiny bit lower, maybe the tires are like, I don't know, ever so slightly worn down and stuff like that. And then there's maintenance, which is your input in this case. So like the U, which was originally like the input, like input vector, now holds like fluids and repair. Fluids might like basically add like 1 unit to like gas and oil, and repair adds like 1 unit to tires and motor. And then your performance is your speed. So your vehicle state and your input will influence your speed. And this, like the A, B, C, and D are essentially the same thing as like the A, B, C, and D up here. These are your trainable parameters. And yeah. So input like goes, input like affects the vehicle state through the matrix B. The vehicle state kind of like affects itself over time, like day t to day t plus one through the matrix A, and like the matrix C uses the vehicle state to get the output, and same like with D, it uses the input to output. So this is kind of how it would look. So you have like day T minus one, and you have your matrix A, which like shows your matrix A takes like the vectors, the state at day T minus one, and applies and then you apply your vector A to get to the current state. And kind of B and C do the same things. Well, not the same things, but they take the input and then describe the current state using the input and then the output and so on. So like take the matrix A, for example, right? So this is not like realistic, obviously, but assume your gas went, the amount of gas you had the next day was like 0.9% of, or sorry, no, not percent, just like 0.9 of the gas you had today. So your gas is going down by like 0.9 of what it was yesterday. And your oil is going down by like 0.05 of what it was yesterday, tires 0.8, and then motor 0.85. So basically your car is degrading really, really fast, right? So what your model essentially, now this, first of all, this is a diagonal matrix. Your A matrix does not necessarily have to be diagonal, right? Like for example, your tires could like if you had good tires, that could ever so slightly reduce the amount of gas used. So there's like a bit more gas in your tank. And then if you had if you had a good motor, or if you had good tires, that could ever so slightly reduce the load on the motor. If you have a slightly better motor. The point is A does not have to be a diagonal matrix. And then the control matrix, which is B, that describes like the input to the current state. Basically, this is just it shows you how how the input affects your current state. So for example, in this case, I'm using like 1. So basically, fluids add like 1 unit of gas and 1 unit of oil when you perform the input. And repair adds 1 unit of tires and 1 unit of motor. You don't have to do maintenance, or basically you don't have to have an input at every single time step. And then your observation matrix is kind of like your C, which is like mapping your current state to your output. So your gas, oil, tires, and motor all kind of affect your speed in this case. The numbers here are like things that I just came up with. When you're actually like working with these matrices, like again, these are trainable parameters, so you're gonna train these. You're not gonna like randomly initialize them as I did here. And D is like your skip connection. Let's just assume that like fluids and repairs add like 0.1 and 0.2 to speed directly. So using your formulas, we have like your current state is equal to, like one part of it is you grab your A matrix and you multiply by your current state, or not current, your previous state, which we describe as x of t minus 1. Let's just initialize it to like all ones. So basically your car starts out at like 1, 1, 1, 1 for gas, tires, oil, and motor. You apply your A matrix first. So basically your car degrades by about like this much on the first day. So this matrix right here, the 0.95, 0.95 one, is about half of your current state. The other half comes from the B. So B multiplied by your input, let's assume your input is just like 0.4 and 0.3. That gets you the other half of like your current state. And then you take these two vectors and add them together to get your current state. That's pretty much it. That's how you go from like your previous state to your current state. And then to get the output at any given state, you simply take your C matrix, and then you multiply this by your current state, which you found from like the first equation, and you get like 1.74. Essentially, these are just matrix multiplications that show you, this is just to give you an example of like how this like quote unquote recurrent mode would work. So of course, realistically, this would have like day t minus t0 and then t1, t2, and then like all the way up to day t minus 1 and then day t. So it's sort of like a recurrent neural network in that case, where you're moving from like one time step to another time step, except all of your time steps are just matrix multiplications and then like addition. So it's quite fast to like just zoom forward through all of these things right now. And next is your convolutional view. So far we had the recurrent view. And now if you remember like convolutions, basically you just take like a kernel, which is like the thing in green, and you multiply that by your current like input. So in this case, if your input was like that, like the zeros and ones, then you would like slide your kernel one by one and get inputs into like your, and get outputs, sorry, into your output vector. So you slide it by one and then you do your multiplications and additions. And this process is called a convolution. So it's essentially just U star V equals W, where W is your output, V is the like V is your kernel, and U is your input. And then so where does this convolution actually fit in your like recurrent view, right? So basically you start with like one, like you start with day zero. On day zero, let's just like you have U0, X0, and Y0 representing your input, your state, which is zero, and then Y0, which is your like output on day zero. And you can find Y0 already just by, using the equation here. We don't have an A yet because this is the first step within our quote unquote RNN. So we simply just do B times UT, or in this case, U of 0, because your input is like U of 0 on the first day. So Y for the first day, Y of 0 is just like C multiplied by XT, which is just B and then times U0. On the second day, it's just Y of 1, which is equal to like C of A times B, where essentially X1 gets like the A from X0. In other words, the change in state happens and it gets the input from B. And you take that and then you add your C times B times U1. Essentially, all you're really doing is just like you first find your hidden state X1 by just following the equation A times X0 plus B times U1. And then you find your Y1 by just plugging in your XT and getting this, or in this case, plugging in your X1. And then you continue this process for Y2. You just find your X2, and then you plug it in your XT, and you get your Y2. And then as you continue this process, you sort of get an equation that looks like this, where your A just constantly increases in power, and your Y of K sort of looks like that, where it's like C times AK times B times U0, and so on. So basically, the reason we talk about one-dimensional convolutions is that you can take your kernel and you can just kind of slide it across and you get your outputs Y0, Y1, etc. So like if you started with this kernel all the way on the right, like your CB would be multiplying your U0 and that would get you Y0. And then if you slide it by one, your CB is now multiplying like U1. And then you add the terms together, you get that, your Y1. And then you slide it one more, you get your Y2, and you keep sliding it until you get your YK. So this is kind of how you can use like one-dimensional convolutions on this. So this process is called rolling and unrolling. So much earlier when I said you can sort of train a state space model as a CNN and then use it as an RNN, this is kind of what I meant. You essentially train it with these like convolutions, which is known to be like very parallelizable and fast for training. And you can use inference on it by just unrolling it. And unrolling is just the opposite process of what I just showed you. So by simply rolling and unrolling, you get fast inference and fast fast training. So how might this look in a neural network, you might ask? So basically, if you wanted to train your parameters A, B, C, and D, your UT becomes your output from your previous layer. So your input is just like the previous layer's output. YT is your output of the current layer. And then you apply your like nonlinearities, normalization, and whatnot, and then you train it. And your parameters are A, B, C, and D, and your step size is delta. Now you might be wondering, does it work? How does this model do? It's not great. So with random matrix initializations, you get 50% on MNIST. You can barely even call that a model. So right now, it's extraordinarily like non-trivial to compute K and compute A. And also right now, we're using one-dimensional vectors for our input and output, UT and YT. What if we wanted multiple dimensions for our input and output? We can't exactly do that yet, can we? So how do we solve these issues? Well, first of all, for multiple dimensions, like the trivial solution is just have an SSM for each like one-dimensional string or one-dimensional vector, and then like kind of put all of these vectors together and then like have a mixing layer or like an MLP. Actually, while I'm at it, how many of you guys have heard of an MLP? Like how many of you guys know what an MLP is? All right, what is it? Okay. Yeah. What?
I don't know.
Oh, okay.
We'll lecture about it last week.
Yeah,
Is it a multi-layer percent?
maybe. Right. So you train like each of this stuff with an MLP essentially, and you get your model parameters. So yeah, as I was saying, the trivial solution is just you take all of your one-dimensional vectors and you kind of put them together and you get a matrix output. So each input channel gets mapped to an H-dimensional hidden state and a one-dimensional output. And nonlinear activations are applied, and then you get a mixing layer, which I'll show you in the next slide. And you have like your independent features and whatnot, and you get an output sequence that's in the form of a like matrix instead of a vector. So this is kind of what it looks like. I'm not going to ask you to like understand all of this entirely right now. But like this part right here, like the independent like S4 SSMs, like this is sort of like the CNN part, which I was showing you earlier. You're just kind of taking each one-dimensional input and output, and you're kind of stacking them all together like that. And then you get your XK, and that corresponds to like one dimension of your layer's output. And then you do something called an emission. And then you have like your nonlinear function, like for example, ReLU or Jello or whatever. And then you have your mixing layer. And yeah. And then you take your UK, and then you map your U prime K at the very end here. This maps this, like this entire thing is one S4 layer. You have multiple of these layers, one after another, obviously. So like this is like the current state, or like the state that you pass on to your next layer. And then you take that like state and then you go forward from there. So emission is basically you're applying like C to your current hidden state to get your output Y. If you remember from like the previous diagrams, like it was like Y is equal to C times like X of T, where X of T is your state. So Y is essentially your output, and you're basically just applying C to your like current hidden state to get your output. And then mixing is essentially like you're taking an MLP and then you're putting all of your layers, like one-dimensional layers together in that MLP. And you're trying to like get each layer to learn about other layers and pass like a usable hidden state onto the next layer. And why do we need this mixing layer? It's to basically capture like information, like you want to capture the information independently per channel, true, but also like you want your information to like kind of like cohesively work together, right? If each thing is kind of just trained independently, that kind of ruins the purpose. So the mixing layer basically allows information exchange across each one-dimensional vector. And yeah, after that, our second issue that we described earlier was the random initialization. When you randomly initialized A, B, C, and D, and then you trained them, you had like 50% on MNIST, which is horrendous. So like there are some explanations to it. The biggest and clearest explanation is that like it leads to vanishing and exploding gradients in your matrix A, because your matrix A is like, well, you're just kind of multiplying A by itself a lot of times really, really fast. Like first it's like CB, then it's CAB, then it's CA squared B, and so on, all the way up to AK. And this can lead to vanishing or exploding gradients, right? So powering up like A like this, like multiplying it to constant like powers like that, also leads to like terrible like computational complexity. It's like H squared times L. H squared being like L being the sequence length, H squared being like the dimensionality, or H being the dimensionality, and then you're squaring that. And it like also suffers from being unable to do long range dependencies, which so the original goal basically failed, right? So how do you solve this? You use Hippo, or specifically, you use the high order polynomial projection operator. And I'm not gonna ask you to like look into the math of this. You're not really gonna care. But basically, the idea is like it allows like compressed representations of like your given input, and instead of storing like all of your past values, for example, it like kind of takes like weighted sums of like your continuous function from before, and uh stores them like compactly. And this also enables like long range memory retention, and it makes your A matrix like a lot easier to compute. So now that you've initialized A to your Hippo matrix, uh, you you have significantly reduced like the computational complexity from like H squared to O of H plus L. So almost linear, right? So this is essentially kind of how your like thing works when it's training. The convolutional kernel uh is basically like this, where you like take your S4 parameters, A, B, C, and whatnot, step size, and then you do your convolution. Uh, all of this you can sort of ignore, except Woodbury identity, everyone's favorite identity. But like, you're not really gonna need to know this much. This kind of just like happens. And the code for this is all like within packages and whatnot. So the only important thing to note here is like before we were using fast Fourier transform, um, and we kind of lost that now, but it's okay because this is still faster, so we don't really care. And so basically, originally our SSM was doing like 50% on MNIST. With Hippo, now it's at 99%, so significant upgrade and usable model. Before we had trouble figuring out what K was, the kernel. Now like not figuring out what K was, but like computing it, because like the memory usage was so high that it was kind of unrealistic. Now with Hippo, it's like H plus L, so like solid. And then in total, your Hippo, like your entire SSM's computation with Hippo is like H plus L, and then log of H plus L. So it's like O of n log n almost-ish, which is a significant upgrade. So now this is our first solid SSM model called S4, and this was published back in 2021. There have been a lot of like, let's just say there's been a lot of papers since then, and there have been like many updates to this, and like people have like completely changed like this idea. Like they've like this has evolved a lot basically. And it's called S4 because like the paper name is like structured state space models for sequence modeling. So it's like four S's. Here are some benchmarks, like this was released like way back then, right? So like obviously you're not gonna find like models you might like be very familiar with here. But for its time, it was like pretty good. It was outperforming like some of the best models. And this is just another benchmark. Like this is with like this is of the sound one. Um Sound was like kind of difficult to process back then. WaveGAN used to be able to process it pretty well. The thing is like it's like WaveGAN is like significantly larger, like 60 times larger or something like no, maybe it was like I forgot exactly how much larger it was, but it was like significantly larger than S4 and its performance is still worse. So like it was pretty good. Uh and like the biggest thing was like the long range arena benchmark, which they frequently talked about. And they basically showed that it was as efficient as like the best like similar parameter size transformers of the time. Not like transformers with like significantly more parameters, but like basically when you took an SSM and a transformer that were of like I don't know, like a couple 100,000 parameters or something like that, like the S4 performed like significantly better. So and then this is the last benchmark here. Like it's got a slightly higher like perplexity score, but like it's way faster in terms of generation than a transformer at this point. So they then came up with something called S5, which is like parallel scans. So it works directly with all like dimensions and uses parallel scans. So before like we were kind of we were kind of doing like we were kind of taking one layer inputs and one layer outputs, or in other words, a vector input and a vector output. Now it's going to turn into multi-layer or rather like higher dimensional inputs and higher dimensional outputs. So first, we have like if you're given like an associative operator like multiplication and a sequence of events like or elements, sorry, not events, like A1 to AL, the scan operation that they talk about basically returns like uh sort of like a like what's it called again? Factorial. Sort of like a factorial of like the thing, and then it returns in like a little list. So how is this useful? Well, that's in terms of multiplication. If it's like some other operation, then obviously it's going to be that operation. So how is this useful? If you take like A0 and B0, where A0 is like your state, like changing matrix one state to the next state, and B is your like input to current state, and you do like your operation, in this case multiplication, with like A1, B1, it gets you this, and you can kind of like use that for like basically getting the next like state within like a certain sequence. So the current state was before, if you remember the equation, it was like x of t is equal to a times like your previous state xt plus like b times your input. This operation, like this thing called parallel scan, uh basically allows you to like pretty efficiently find it. So one big benefit is this allows for time varying uh parameters in your SSM, meaning like before A, B, C, and D were fixed parameters that you would use regard like over that they were fixed parameters, and these parameters would stay fixed throughout the entire inference. Now the parameters can change through time, and this can be useful uh for like this can be useful for like any sort of input that requires your parameters to change over time. And the biggest benefit happened in language generation, and that was kind of where the big change happened here. So parallel scans is like very easily parallelizable, which is important because we can now do something called like multi-input, multi-output. So we can take like your original equations, xt is equal to like that, and then your yt output. And we can change the dimensionalities of B and D to get like multi-input, multi-output sort of inputs xt and outputs yt. So now like your hidden state size has decreased. And this means you can apply parallel scans way more effectively. And since your dimensions are mixed, you don't need another mixing layer at this point. So your your input and output are essentially like more than one dimension. Like they're essentially matrices instead of vectors at this point, and you don't need a mixing layer to figure out like how the different like vectors interact with each other. So this is essentially what an S5 layer looks like. It's essentially you have your big like matrix A and B, and you have your emission and nonlinearity, and you've basically removed the mixing layer. And you can just get your layer output directly. So now you might like the only thing missing right now is like selection. And that's kind of the only thing that a transformer has over like uh over state space models right now. So input dependency is kind of what it is. And so the core idea for S6, which adds like the selection S to it, it basically improves SSMs by having input dependent matrices. So like in self-attention, for example, your attention scores change dynamically based on like the input tokens. And now with S6, your state space parameters, A, B, C, and D, are changing dynamically based on your input tokens with selection. And S6 is Mamba. So we're going to get into that more next lecture. And the main like formulas for S6 changed. You now have your input parameters UT next to every single like A, B, C, and D parameter from earlier. And A, B, C, and D changes based on UT. So yeah, next lecture, we're going to be expanding on Mamba, and then we're going to go over Mamba 2's paper. And Mamba 2's paper, the paper title is literally Transformers are SSMs. And it kind of goes over a proof on how they derive like the key query and value matrices from A, B, C, and D. And we'll go over current applications of Mamba 2 as well. Right now, Mamba 2 is kind of being used in hybrid models a lot, and the performance is like pretty good. And if time permits, we might discuss like Google's new Titan paper and how it relates. So yeah, that's about it.